Hi, this is going to be part 2, going through A-Level Further Maths, Year 1, Chapter 9 on vectors. So in part 1, we looked at some basic stuff, the dot product and the basic equation of a line. Most stuff we're going to do today is going to focus on planes, which is basically a 2D flat surface in 3D space. The best way to think about it is like an infinitely big piece of paper. That's basically what a plane is. Perfectly flat, perfectly thin, but goes on forever. I need a few new terms. I'm going to go through a few new skills before I get into this. First new term comes up tons for this is the normal vector. The normal vector for a plane is going to be the vector that points out from it at right angles. So for example, if I try and draw this, that's your normal vector, where it's at right angles to the whole plane. You've got a few choices. This vector can be basically as big or as small as you want, as long as it's at right angles. And of course, it can go either above the plane or below the plane. No matter how you do it, that's still a normal vector. We have another definition, which is a unit normal vector. This is the same idea. You've got a normal vector, so it's at right angles to the plane. However, if it's a unit normal vector, then that length of that vector must be 1. Okay, we're going to see that skill first. So we're going to normalise these following vectors. So when I say normalize vectors, you're basically making them into unit vectors. You make them have a length of 1. So if I look at my first vector, I have the vector 3, 4. If I want to work out the length of this, that's the magnitude, we use Pythagoras. Okay? Because basically I'm going 3 squares along and 4 squares up. I want to know what this length is going to be. To do that, that is going to be the square root of 3 squared plus 4 squared. That's going to be the square root of 25, which is 5. So this vector here has a length of 5. That means we can write the normal vector is going to be 1/5 of the original vector. Okay, and if you notice what I've done here, this is actually called a hat. You give it a little hat, which is like a little triangle, and that denotes that's a normal vector. So if you have a vector with that hat on, that means its length is 1. Okay, which is sometimes really important. We'll see more exactly when, probably in another part of vectors. Next, same idea for this size vector. So again, you want the length of it. So we're doing Pythagoras. So it's going to be 2 squared plus minus 2 all squared plus 1 squared. You work it out. 2 squared is 4, so it's 4 plus 4 plus 1. This is root 9 or 3. So this vector has a length of 3. So therefore, it's going to be 1/3 of the vector 2 minus 2, 1. And again, typically, these would end up being square root numbers. I've just picked a few examples so they have whole number square roots. But typically it's something like 1/the square root of 20, and then your vector goes down here. Okay? And again, the idea keeps on working about how big your vector gets. It will be the exact same idea. You would do 10 squared plus minus 4 squared plus 2 squared plus minus 1 squared, add them all together and root them all. Second skill, we have what's called the cross product. So we saw in part 1 that was the dot product. Let's go through that first. Here I've got two vectors A and B. If you do A dot B, you're just basically timesing the numbers in the same position together. So first you times together these two numbers, then you times together these two numbers, and then you times together these two numbers. So 1 times minus 3 is minus 3, 2 times nothing is nothing, and nothing times 2 is nothing. So here, A dot B is minus 3. And then we saw the really important thing, that if A dot B was 0, it meant the two vectors were perpendicular or at right angles to one another. Okay, that's fairly straightforward to work out. What we're going to look today is going to be the cross product. Okay, this is slightly harder, and it actually follows on from working out the determinant of a 3x3 matrix. Okay, so I did an earlier video on that. Go to that if you're not sure on it. But if we want to work out the cross product, as literally A cross B as a multiplication sign, we're going to use it by doing a determinant. So the way this works out, you have to be quite specific how you lay it out, and then it's fairly straightforward. Along your top row, you want I, J, and K. I think I mentioned this before. I, J, and K basically specifies 1 unit in the X direction, 1 unit in the Y direction, and 1 unit in the Z direction. So basically they're unit vectors, vectors of length 1, in the x, y, and z directions. For your second row, you want the vector A, and it's always which comes first takes this second row. So here it's 1, 2, 0, you slide it in across. And along my third row, I need my vector B. So minus 3, 0, 2. Now we're going to work out the determinant, and that will give us A cross B. And the way to work it out is you basically want to expand this determinant along this top row. Okay, let's go through that. So this will equal I, and then I have to times that by. Remember, for the determinant, we work out I, we then cross off the row in the column, and it's the determinant of what's left. Next we have minus j. Remember, it goes plus, minus, plus, minus, plus, minus, so we need minus j, and that's times by the determinant of everything that we're left with. So let's circle j, cross off the row and cross off the column, and it's minus j times this determinant of the entries that are left. Then we're back to plus k, do the same thing again, cross off, and we are left with 1, 2, minus 3, 0. Now let's work that out. Determinant of this is just going to be 4, 2 times 2 minus nothing, so I have 4i. Determinant of this is going to be 2 minus nothing, so minus 2j. Determinant of this is going to be nothing minus minus 6, so plus 6k. And that is that cross product. And again, normally you can write this back in vector form, where the i's go at the top, the j's go in the middle, and the k's go at the bottom. Okay, and that is your cross product. Okay, that gets to be really important. What makes this really useful, and we'll see more why in a second, is the fact that this cross product vector will always be perpendicular to both A and B. Okay, and that tends to be really key in like 10 minutes time. Okay, let's go through like a quick example question. So questions normally look something like this. So here we've got two vectors, A and B. We want to find the vector C, which is A cross B, and we want to verify that C is perpendicular to vectors A and B. So let's go through the cross product again. So determinant of a 3 by 3 matrix. Along the top row you have I, J and K, which are the unit vectors in X, Y and Z. We want A first, so we then slide A in, 3 minus 2, 4, and then we put B in. This will then equal I times, first I want the determinant of this, so that's minus 2 minus 4, so I times minus 6. Now it's minus j, let's put that in brackets. Now it's minus j, and that's going to be times by the determinant of this. So that would be minus 3 minus nothing. Put that in brackets as well. Then we want plus k times, and it's going to be the determinant of this bit here, which will just be 3 times minus 1 minus nothing, which is 3. And that is my cross product. So plus 3j and plus 3k. So that's going to equal minus 6, 3, 3. Just an aside, most questions you can divide through by these. Okay, here we wanted to work out the vector C, which is A cross B, so we can't divide by it. But if we just want a perpendicular vector, or a vector that's normal, another word for perpendicular, to both these vectors, there's no reason we can't take out the common factor of 3 here and have it as minus 2, 1, 1. This question we can't, so just work out the cross product. Don't do anything with it, just work it out. But normally you can divide by common factors if you see them. And yeah, just to reiterate, whenever you see the word normal, I think you've seen it before in regular maths, that also means perpendicular. Okay, we have found our cross product. Let me just drag that across. We now want to verify that this is indeed perpendicular to vectors A and B. So to tell if two vectors are perpendicular or at right angles, we use the dot product. So we're going to do A dot C. So sometimes I underline these. That's basically notation for saying they are vectors. Because typically when you see vectors in exam papers, they have them in bold font to make it clear they're vectors and not numbers or letters. Okay, A dot C. That is going to be 3 minus 2, 4, dot minus 6, 3, 3. Let's get rid of this for now, so I remember what it is now. Working this out, 3 times minus 6 is minus 18, minus 2 times 3 is minus 6, and 4 times 3 is plus 12, which of course doesn't work. Let's see what okay, sorry, if you saw my mistake earlier, I worked out this bit incorrectly. I did a determinant of this, which should have been 2 take away 4, so it should have been minus 2, not minus 6. So this is minus 2y, which then changes this to a minus 2. That then gives me minus 6 plus 12 equals 0, which means A and C are perpendicular. We then do the same with B dot C. So B is 0, 1, minus 1, dotted with minus 2, 3, 3. And that is going to be 0 plus 3 minus 3, which again is 0. Okay, so it can be useful to check to make sure there are any mistakes, to check that these vectors do indeed end up being perpendicular to your two starting vectors. Okay, if it's not, you have made a mistake like I just did there. Okay, after that embarrassment, let's move on. On to actually finding the equation of the plane. There are two forms for this. Okay, there's a form that's really easy to work out, and also a form that's really useful for working out questions. Sadly, they're not the same. To work out any equation of a plane, we need at least 3 points on that plane. Okay, that's the minimum we have to define a plane. Let's do this the easy way. We're going to use basically the same method we used to define a line. So first we're going to pick any point to start off with. I'll pick this one down here. So I'm going to say my starting point is 10, 0, 0. And then I'm basically going to define two lines. I'm going to define one line that takes me to this point, and one line that takes me to that point. So plus lambda, I want to get to this point here, and the vector from here to here is going to be this vector minus this vector. So that would be minus 10, 0, 4. Okay, so here you can see if lambda is 1, that would take me to this point here. So it would be 10 minus 10 with a plus 4 here. Next, I'm going to do the exact same thing. I'm going to ignore this term for the time being. I'm going to work out the direction vector from here to here. So doing 5, 11, 0, take away 10, 0, 0. That's going to give me minus 5, 11, 0. Okay. And you can see here that if lambda's 0, if lambda's not here, and mu is 1, it gives me this point here. So it'll be 10 minus 5 is 5, nothing plus 11, and nothing plus nothing. And this equation defines the plane. Basically, as you change lambda and mu, you're basically going to move along that plane. And I think that's pretty much it for this form. Hopefully you find with that idea. A quick way to remember it is because this plane is a 2D shape, you have two separate independent letters. Okay, that's where I tend to remember it. Okay, that is one form. We also have an alternative, better form. So the problem with this is you basically got lambda and mu who can both be any value they want. That means when working anything out, you've got so many combinations to work through. We have this slightly more compact form where we've got r dot some vector equals a constant d, where d is just a number like 12 or 0. And it turns out here, which shouldn't be a massive surprise, this n represents the normal vector. Okay, and again, it's any normal vector, not the unit normal vector. Any normal vector you want can be that n. So to work this out, we need to find out our normal vector. If we want to work out our normal vector, we're going to use these vectors we just found out. We know we've got one vector here, which was minus 5, 11, 0. And we had another vector here. These are both direction vectors, so take us from one point on the plane to another point on the line, whereas this was a position vector, it gave us the position of a point. So if you want to work out a perpendicular vector, you need to cross your two direction vectors. So basically we need to cross these two vectors. And that will give me a vector that is perpendicular to both of these, which of course will be perpendicular to the plane, because those two direction vectors together define the plane. So yeah, that would be perpendicular to both of these. Okay, let's do that. So our normal vector is going to be minus 10 cross with minus 5, 11, 0. We're then going to work it out again. For that, we use the determinant of a 3 by 3 matrix, and I'll try to get it right this time. So that is going to be I times by the determinant of this matrix. So that will be I times minus 44. We've then got minus j times the determinant of this matrix. That will be nothing minus minus 20. So minus j times 20. And then lastly, we're going to have plus k times the determinant of this vector. So plus k times, and this one is minus 110 minus nothing. Okay, that's it. We can clean it up a tiny bit. We've got minus 44i, minus 20j, and minus 110k. And back in column form, that's going to be minus 44, minus 20, minus 110. Okay. Here, like I said earlier, we can divide this whole thing by 2 and it won't change anything. We can also flip all the signs to positives and it won't change anything. They're still going to be normal vectors. Doesn't matter how big it is, what direction it points in, it's going to be the same normal vector. And in fact, to make my maths a tiny bit easier, I'm going to divide this whole vector by minus 2. So it just gives me a slightly more manageable vector in this form. Our numbers are a tiny bit nicer. And again, it's always nice working with positives. So we want it in the form r dot n equals d. And we have worked out what n is. So we now know it is r dot 22, 10, 55 equals d. R defines any point on my plane. Okay, so we're not going to work out what r is because that's like when you have the equation y equals 2x plus 1, to work out r is trying to say to work out y. It's just a variable, it's always going to change, and it defines any point on my line. What we can work out though is d. D is roughly basically a measure of how high this vector is. So basically, if I had another parallel vector, another parallel plane, that was the same plane but a lot higher, it would just have a bigger value of d. That's kind of what d tells you, roughly, not kind of exactly or really logically, but to get your head around it, it defines how tall that plane is. To work out d, all we need is any point that we know is on the plane. So I can pick this point that we're told in the question is on the plane. So we know that 10, 0, 0 is on the plane. And if I plug it into this equation, if I let r equal 10, 0, 0, because r is any point on the plane, we can use that to work out d. So 10, 0, 0 dot 22, 10, 55 will equal d. We can then work out d. Working out this dot product, we have 220 plus nothing equals d, which therefore means that d is going to be 220. We've now worked out d and we can say we are finished. We write down our final form, which is the equation of the plane in this form, looks like this. Now I know this was a lot more effort to work out, however, for basically solving any kind of problem, this form is a lot easier and a lot more helpful. Okay? If you're stuck with it in this form, solving all problems become quite tricky and quite challenging. Okay, and even some question exams will say go from one form to the other. So it's useful to know how to do this. Just a quick show of an exam style question. So a plane, this symbol here is capital pi. So it's like pi but in capital form, or what they tend to use for planes. So a plane pi has a normal vector of 2, minus 2, 1 and passes through the point 5, 0, 2. We're going to find an equation of the plane in this form here. So straight away, we know the normal vector. So we can plug that in, and that equals d. We don't know d yet, but we can work out d by plugging this point in. Again, r is any point on my plane. So whatever point on your plane you put into this equation, you will always get the same value of d. So what I mean is, if I go back to my previous slide, I picked this point to work out D. If I picked either the other 2 points, either 0, 0, 4 or 5, 11, 0, I would always get the same answer for D. Okay, that's why this method works. So you pick any point on my plane, and that'll give us the one and only value for D. So working this out, 5 times 2 is 10, nothing times minus 2 is nothing, and 2 times 1 is 2. Which therefore means that D equals 12. And the equation of my plane is r dot 2 minus 2, 1 equals 12. And that defines all the points on my plane. Oops, sorry. Okay, last exam style question. We want to work out whether or not these 4 points are coplanar. So coplanar just means they're all on the same plane. To do this, we're going to work out the equation of a plane for the first 3. We're going to work out what plane these 3 points lie on, and then see whether or not this point is also on that plane. So let's get started. I'm going to put this in the easy form first. So I start with any point, and I'm going to define 2 lines. So first, I want the direction vector take me from here to here. So if I do this vector minus this vector, that gives me that. And that'll take me from this point to this point. I'm going to do the exact same thing. I want the direction vector that takes me from this coordinate to this coordinate. So I do this, take away this, which is 2, 1, 2. Okay, that's an equation of the plane. We've kind of got 2 choices here. If we write this in the other form, it is super easy to tell whether it's coplanar, but it takes a bit of time to do that. Or we can just try and see whether or not this is coplanar. Okay, which is a bit more work, but we don't have to step in the middle. Just for practice, I'm going to put it in the new form. And in terms of time, there's not a huge difference. So normal vector, we work out by doing the 3×3 determinant of the 2 direction vectors. Okay, let's try and go through as quick as I can without making a mistake. So this will be I times 6 minus 4 minus j times minus 6 minus 8. Minus 6 minus 8 is minus 14. Plus k times minus 3 minus 6. So minus 9. Let me just check that. We had 6 minus 4. We had minus 6 minus 8, and we had minus 3 minus 6, yeah. So that means my normal vector, I have 2i, I have plus 14j, and I have minus 9 for my k's. So the form is now going to be r dot 214 minus 9 equals d. We know it went through the point 2, 0, 0. So 2, 0, 0 dot 214.9 equals d. These terms both vanish, which means that d must equal 4. So we now have the we have the hard equation for the plane, but that's so much more useful for solving questions. Okay, let me copy that and drag it up. So now we need to see whether or not this point is also on the same plane. And the way we're going to do that is we're going to plug it in. We know that for every single point on the plane, so we did it for these 2 or anything in between, if we plug it in this equation and do the dot product, it will always equal 4. So we're going to plug in this extra point and see whether or not that dot product gives us 4. If it does, it is coplanar. If it does not, then it is not coplanar. It is not on the same plane. So we have 2 minus 2, 1. 2 minus 2, 1. Dotted with 2, 14 minus 9. And at first glance, this is nowhere close. 2 times 2 is 4. We then have minus 28 minus 9, which is nowhere near 4. Minus 28 minus 9 is minus 37. Add the 4 is minus 33. This does not equal 4. So therefore the points are not coplanar. And again, that means that all 4 points are not on the same plane. For this method, it doesn't matter which 3 points you pick first to make a plane. All you're going to check is whether or not that 4th point is on the same plane. And that's your definition for coplanar. And that is it for this part of vectors. I've written some fun questions to try. So it starts with normalizing, then find the equation of a plane going through 2 points in both forms, and then a couple of exam questions that I talked through kind of how to do them just now. Okay, I hope that made sense, and thanks for listening.